Welcome to Section 1 Introduction. Embracing Incomplete Recovery. Incomplete recovery is a powerful tool in the arsenal of a database administrator. It allows us to restore a database to a specific point in time, even if we don't have a complete backup. This is particularly useful in scenarios where a database has become corrupted, a transaction has been accidentally committed, or we need to rewind the database to undo a series of changes. Unlike complete recovery, which restores the database to its most recent consistent state, incomplete recovery offers granular control over the recovery point. Imagine a scenario where a faulty application update inadvertently introduces erroneous data into your database. You need to revert to a point before this update wreaked havoc. This is where incomplete recovery shines. It allows you to pinpoint the exact moment before the update and restore the database to that state. This capability proves invaluable in mitigating the impact of errors and ensuring data integrity. However, incomplete recovery is not without its nuances. It's a complex process that demands precision and a thorough understanding of your database system. The steps involved, from identifying the recovery point to verifying the restored data, must be executed meticulously to avoid further complications. This guide serves as your roadmap to mastering user-managed incomplete recovery. We will delve into each step of the process, providing clear instructions and highlighting crucial considerations. Remember, a successful incomplete recovery hinges on careful planning and execution. Moving on to Section 2, identifying the recovery point, setting the stage for recovery. The first crucial step in user-managed incomplete recovery is pinpointing the precise recovery point. This is the specific moment in time to which we aim to restore the database. The selection of this point depends entirely on the situation at hand. If a rogue transaction has corrupted your database, the recovery point would be the instant before the transaction was executed. Conversely, if a faulty application update is the culprit, the recovery point would be the moment before the update was deployed. You can determine the recovery point using various methods, depending on your database system. In Oracle, for instance, you can leverage flashback logs or transaction logs to identify the desired point in time. These logs provide a detailed history of database activity, allowing you to pinpoint the exact moment preceding the error. Once you've identified the recovery point, it's crucial to note the corresponding system change number, SCN, or log sequence number, LSN. This numerical identifier acts as a marker for the desired recovery point and is essential for executing the recovery process accurately. Now let's discuss Section 3. Precautions. Shielding your database from further mishaps. Before embarking on the recovery process, it's paramount to take precautions to prevent further damage to your database. This involves creating a backup of the current database state, even if it's potentially corrupted. This backup serves as a safety net, allowing you to revert to the original state if the recovery process encounters unforeseen issues. Next, ensure you have a copy of all necessary redo logs. These logs contain the information required to replay transactions and restore the database to the desired recovery point. Depending on your database system, you may need to archive these logs to a separate location to ensure their availability during recovery. Finally, it's crucial to perform the recovery process in a controlled environment. This typically involves using a test or development database that mirrors your production environment. This approach allows you to test the recovery process without jeopardizing your live data, minimizing the risk of unintended consequences. Lastly, we reach Section 4, mounting the database, preparing the ground for recovery. With the necessary precautions in place, the next step is to mount the database in recovery mode. This essentially prepares the database for the recovery process, allowing you to apply redo logs and restore data to the desired point. The process of mounting a database in recovery mode varies depending on your database system. In Oracle, for example, you would use the command followed by the command. This sequence instructs the database to start in a special mode where recovery operations can be performed. Once the database is mounted in recovery mode, it's inaccessible to users. This is a crucial safety measure to prevent any modifications to the database during the recovery process, ensuring data integrity. Section 5. Applying redo logs, breathing life back into your data. With the database mounted in recovery mode, The next step is to apply redo logs to roll forward transactions and restore data to the chosen recovery point. This involves feeding the database with the redo logs, allowing it to replay transactions and rebuild its state incrementally. The method for applying redo logs depends on your database system. In Oracle, you can use the command to apply redo logs automatically up to the specified SCN or LSN. Alternatively, you can manually apply redo logs using the command, providing granular control over the process. During this stage, the database meticulously replays transactions recorded in the redo logs. This process gradually rebuilds the database's state, bringing it closer to the desired recovery point. The progress of redo application is typically displayed in the database log files, allowing you to monitor the process. Section 6. Performing the recovery, the culmination of our efforts. Once the redo logs have been applied up to the desired recovery point, the actual recovery process can commence. This involves issuing a command to finalize the recovery, signaling to the database that it has reached the target state. In Oracle, the command is used to complete the recovery process. This command instructs the database to stop applying redo logs and prepare for opening. Once this command is executed, the database is in a consistent state, reflecting the point in time identified as the recovery point. It's crucial to understand that incomplete recovery does not restore the database to its most recent state. Instead, it restores the database to the specified recovery point, leaving any transactions that occurred after that point unapplied. Section 7. Opening the database. Unveiling the restored data. After the recovery process is complete, the database can be opened for normal operations. This involves issuing a command to transition the database from recovery mode to its regular operational state, making it accessible to users. In Oracle, the command is used to open the database after recovery. The option signifies that the database logs have been reset, marking a new starting point for transaction logging. Once the database is open, users can access and modify data as usual. It's essential to communicate to users that the database has been restored to a previous point in time, as they may notice that recent changes are no longer present. Section 8. Verifying success. Ensuring the integrity of our recovery. After opening the database, it's crucial to verify the success of the recovery process. This involves thoroughly inspecting the database to ensure data integrity and confirm that it has been restored to the desired state. Begin by comparing the current database state to a backup taken before the issue occurred. This comparison helps identify any discrepancies and ensure that the recovery process has accurately restored the data. Additionally, review database logs for any errors or warnings that may indicate problems during the recovery process. Next, perform data validation checks to ensure that the restored data is consistent and accurate. This may involve running queries to compare data values, checking data relationships, and verifying data constraints. Section 9. Testing procedures. The importance of practice runs. The importance of testing cannot be overstated. Before performing incomplete recovery on a production database, it's essential to thoroughly test the procedures in a non-production environment. This allows you to refine your process, identify potential issues, and ensure you're well prepared for a real recovery scenario. Create a test environment that closely mirrors your production database, including data structure, size, and configuration. Simulate the scenario that requires incomplete recovery, such as a corrupted database or an erroneous transaction. Execute the recovery process step by step, carefully documenting each action and observation. This practice run provides invaluable insights into the nuances of incomplete recovery, allowing you to fine-tune your approach and minimize the risk of errors during a real recovery scenario. Regular testing also helps build confidence and expertise in handling incomplete recovery situations effectively. Section 10. Conclusion. The power of incomplete recovery. User-managed incomplete recovery is a powerful technique that provides granular control over database restoration. It empowers database administrators to rewind the database to a specific point in time, mitigating the impact of errors, corruption, or unintended changes. While the process involves intricate steps and demands precision, mastering incomplete recovery is an invaluable skill for any database administrator. By understanding the underlying concepts, meticulously executing the recovery steps, and diligently verifying the restored data, you can confidently leverage incomplete recovery to safeguard your database and ensure data integrity. Remember, thorough preparation and rigorous testing are crucial for success. By practicing incomplete recovery in a controlled environment, you can hone your skills, identify potential pitfalls, and ensure a smooth recovery process when it truly matters. With careful planning and execution, incomplete recovery becomes an indispensable tool in your database management arsenal.